Continue our video regarding the design of insertion loss method for the filter design. Before we go any further for designing the Chebyshev or Butterworth type of filter, let's look on the prototype normalized circuit for the low pass filter. So here this case for the basic uh, maximally flat filter. We look in the first case. So I believe all of you have seen the derivation or, for example, the basic circuit of a prototype, where which include of inductor and parallel capacitor. And here we have the load, and here we have the source of the resistor or impedance, which normally we normalize it into 1. And if we look, if we want to analyze the input impedance, okay, we look from here, okay, we analyze the Zin, and we have the Zin equivalent to this equation. And from here also, we can analyze the gamma, where gamma is Zin minus 1 over Zin plus 1. And if we include all this value in the power loss ratio, for example, for the maximally flat here, okay, and we compare with this equation of power loss ratio, compare with this, and from the derivation, we will get that L equivalent to C, which is equivalent to square root of 2. And here R is equivalent to 1. So this is the value that we get for the basic low pass filter for the prototype circuit. So here, the source and the load resistance will be 1 ohm, and the omega C is 1 radian per second. So this is the normalized prototype circuit without scaling. No frequency scaling, no impedance scaling, with no conversion to the high pass filter or band pass or band stop filter. So in designing the basic filter, you must design this normalized prototype circuit first before you going further for the advanced design of the filter. And from that, we have two topologies for low pass prototype circuits. Either you want to design the low pass filter based on this form, okay, the first one, which is start with the capacitor, then inductor, or you can start with inductor, then capacitor. So either one is also okay. But normally in this course, I don't know, maybe following the book, so most of the design are following this structure. Okay. And here, example of values for maximally flat low pass filter prototype tables, where, okay, we have n here. N is a number of the order of the filter. So if n equivalent to 2, for example, we have the, okay, we will look at this. If n equivalent to 2, okay, the for example, capacitor value is 1.4142, which is square root of 2. Is it correct? And inductor also 1.4142, and the resistor value is also 1. So this is the basic prototype circuit for low pass filter. And from then on, you can design the further increase of the number of order of the filter. The higher the number of order you choose, you will have a very good characteristic of the filter. That means maybe you have a good cutoff frequency and good attenuation for the design, which is near to the what we call the near to the perfect filter. But you will increase the cost, which increase the number of elements in the circuits, which also increase the complexity of the circuits. So here in the graph, okay, so G1, G2, G3, G4, which is representing the GK. So this the whether you can choose for inductors or capacitor value for this prototype circuit. So tables are important in order to determine the prototype circuits, whether you want to use the maximally flat or equal ripples or other types of filter. Maximally flat normally use only one table, but equal ripple will have maybe many types and many more tables because they based on the ripples. Maybe 0.5 dB ripple, maybe 1 dB ripples, maybe 3 dB ripples based on the tables. So the example of tables for equal ripple, or what is and this is not equal ripple, this is for the maximally flat. Maximally flat. Okay. So normally maximally flat will have all the resistor value at the end will be 1, which is at the load, which is the source and the load will be the same. For equal ripple, okay, for example, the table here is the specific table for 0.5 dB. This is for 3 dB. And this graph is, I think, maybe for 3 dB. I'm not sure. Okay. So if you can see that at the load, when it is n equivalent to odd number, okay, so the load will be 1, which is the same as the source for the odd number. But for the even number here, okay, the even number, so the load will be different. So be careful with this. This may be some related in the question. So you still need to calculate the load because at the even number of order for Chebyshev type, so the load will be different. After you have designed the prototype, now we want to scale or transform it to the real value. So we want to scale it into the impedance and frequency. Let's see the first one, which is the impedance scaling. So since the filter is a linear circuit, we can multiply all the impedance, including the terminating resistance, by some factor without changing the transfer function of the filter. Of course, the input and output impedance will change. So here we want to calculate the desired source and load impedance, we want to calculate the inductor, capacitor, source resistor, and load resistor. For inductor, so we can calculate XL. We start with R0, just multiply by XL. And we have equivalent to omega R0 L. And therefore, if we want to have the inductor value, so we have the new inductor value is R0 times L. And for the case of capacitor, okay, so capacitor is dividing the capacitance value over R0. For the case of source impedance, so it's just multiply by 1. Okay, and we got the R0 is 50 ohm, so this 50 ohm. But for the load, so normally RL, you can see from graph, for especially on the equal ripple, is not always 1. So you need to multiply it. So normally, for the equal ripple, if even number n, so it will be equal to 1. But for the case of not even, for odd number, it's equal to 1. For even number, it is not equal to 1. So you need to multiply this. So this for impedance scaling. For the frequency scaling, as you already know, for the normalized prototype, so we have scaled it into omega c equivalent to 1 radian per second. So now we want to scale it to a desired frequency that we want. To scale for different low pass cutoff frequency, we must substitute omega with omega over omega c. So from this, we have XL from the basic XL on equivalent to omega L. Then we replace it with the L over omega c. Okay, so therefore we will have the new L is L over omega c. For the case of capacitance, so capacitance is 1 over omega c. We replace with omega c over c. And therefore, we have the c prime equivalent to c over omega c. And when we include both the impedance and frequency scaling, so we got the new inductor value, Lk equivalent to R0 Lk divided by omega c, Ck prime equivalent to Ck over omega R0. So the new source value equivalent to R0, and the new load will be R0 times RL. So for the impedance, you don't need to multiply with the frequency. Please note that the frequency is only valid for the inductor and capacitor. You know what? Because some previous students, they also multiply with their frequency. So with the next video, we will see the example of the frequency design of the basic filter.